All right, so I'm recording right now, so we can start. So let's begin our lecture. Any question from lecture one before we go through reviews? Any questions about the class format or what's my expectation or anything? Because a quick warning, assignment one is going to be released on Wednesday. You have 3 weeks on it. The way I break down the three big assignment is inside each assignment there will be a checkpoint where we'll spend about half of the class time instead of having an in-class exercise. We will actually go through and you do a quick demo for the checkpoint. It won't be the full assignment. It will be some fraction, basically a fraction of the code that I expect you that hey, by this time about halfway through the assignment deadline, you should hopefully be able to do this much, because once you are able to get to that point, the rest of the assignment should be pretty straightforward. If you cannot, it means that, okay, we'll spend that 1 hour trying to figure out how you can actually progress and make sure you reach the goal. All right. So yeah, assignment one should be released basically Tuesday night. By Wednesday morning, you would have time to look at it. You can ask questions right away on Wednesday, the class on Wednesday. I sent out the one more thing. I sent out the survey. Now please fill them in. I will use your availability for any potentially any additional makeup class, which I will announce the actual day once I know what works for all you guys. These slots will be used for the one we missed on last Monday. And I think there are 2 more holidays. So many holidays on Monday. But I think that there'll be 2 more holidays in this semester, which we'll need to do makeup class. The way it would work is, no, don't jump here. Sorry, I have a cat with me right now. They are both being quarantined because they just flew from the US. Don't jump on my keyboard, please. So yeah, if you cannot send exercise one, what do you mean? Oh, you cannot submit. Let me double check that. Okay, let me do it right now. Share, because I have it on anyway. Go sleep, cat. Please, come on. Okay, let me edit real quick right here. Yep, online submission, text entry. All right, I saved it. You should be able to submit it now. I'm so sorry about that. For the first in-class exercise, I hope whatever you type in, you can just copy and paste. And again, the reason behind it, okay, that's why I'm so confused. Like I don't see any submission so far. You should be able to submit it now. Any other questions? Okay. Hopefully, if I type something weird, it's probably her, not me. Let's see. Here we go. All right. If this is too disruptive, I'll put them into another room for now. Let me know if that's too disruptive for you. If there's a good distraction where it makes you feel awake or whatever, I hope let me know as well, whatever you prefer. All right, so lecture one, we talk about how computer works, and we talk that, hey, this class will go deeper into trying to understand whatever you buy, right? Whatever you buy, when you buy a desktop, when you buy a server, you hopefully know what goes in there, right? So here right now, we'll take a deeper look, right, as I said, into the processing part, the CPU, the DRAM part. This is actually the second half of the class. We are not going to talk about I/O that much. This I/O thing is the content of the OS class. Basically, what happens when you have to manage input and outputs and everything to make sure your computer runs properly with keyboard and mouse. We will talk about how data gets transferred over between I/O and memory and processing. If you take system skill class or file pro, like this is basically the same class, you would then notice that the IO basically is where your program's assembly code is stored. And when you actually run it, you copy that from the IO to the memory, from storage device to the main memory, right? And we talk a little bit about the age of Moore's law, right? The reason behind that is because there's the big importance in terms of what you can fit inside this chip. If you buy a CPU, you'll notice that they have certain size, right? How big is a CPU these days when you buy it? Anyone seen it before? Like roughly how many centimeter by centimeter? Anyone want to take a quick stab at the size? So basically, it's like around, yeah, something like a little bit less than 10 centimeter by 10 centimeter, right? Which means that it's 2D thing. It means that all the transistor that you want to put in for your chip has to fit that 10 by 10 centimeter, right? And Moore's law said that, hey, if you look at the plot on how many transistor you can cram into this 10 by 10 centimeter, you can go that rate in a couple of years for that, right? So it kind of like set the trend saying, hey, every 2 years you should be able to see the processor get faster. I'm not saying the performance double. I'm saying they get faster. Usually you're looking at around like 10% range, right? 5 to 10%. And that's a lot because over time, if you multiply 1.05 together all the time, it actually can double eventually the performance pretty quickly. Uh, and we talk about what happened when you run a simple code like this, right? In I equal 10, j equal 20. It starts from the program, which then compile into assembly, right? In these most of the machine, if you run it on your desktop, it will be x86. In MacBook, it will be x86. In the next year, I think there might be some ARM ISA showing up, popping up on MacBook. So it basically interact with the runtime and the ISA. You talk about what the heck is ISA today. And from that point on, you move on to the microarchitecture. Starting from next lecture, how do we design a CPU? Right? And then we talk a little bit about the von Neumann model, where everything is stored inside your DRAM. When you run a program, the program itself gets stored in DRAM. Let me draw this quickly. Basically, this is your memory. Von Neumann basically said this. This is your program, and this is where your data is. They all share the same thing. The same physical, we'll call from this point on. From this point on, we'll call this physical memory. Why physical? When you buy DRAM, it's a real thing that exists. It's that stick, the memories that you plug onto your mainboard. That's why we call it physical memory. There are two key properties. The program is stored there and the data is stored there. And you do instruction processing. Instruction processing means you process your assembly code by line by line by line. And we can compare that against the Dataflow model, which is instead of doing things in control flow order, line by line by line, you switch to a different line only if you run into things like for loop or if else. Right? For loop, you go back to the first line on your loop. If else, you go to either if go here, else goes here. Dataflow model means that you look at everything as a function. If all my inputs becomes ready, I run it right away, right? So it compute whenever operands are ready, and there's no instruction pointer. In this class, we'll go through what instruction pointer means. You actually design a simulator that deal with the instruction pointer. So by the end of this class, I hope you understand what the instruction pointer do. And when you convert one assembly code into another assembly code or one assembly language to another assembly language, the hardware kind of follow the same logic. In this class, we'll use one ISA, which is way more simpler than x86, to learn how to design a chip. And that knowledge will translate over to real ship that you can use nowadays, right? Ordering in Dataflow model is based on Dataflow dependence. And then think of it as if this is a math function. Whenever input is ready, you can run it. It's as simple as that. And this allows many instructions to execute at the same time, which if you take OPL or parallel programming, I'll also stress this slide. So this is where you get performance. That's where you get the parallelism. If you run on a GPU before, you see that too. Sorry for the animation bug from last week, which exists and persists here. Basically, these are the comparison between the two, right? In here, the left is sequentially done line by line by line. The right can be done in parallel. The plus and the multiply, the first two lines can be done in parallel because there's no what we call dependency. I have A, I have B, I have 10. I can do them both at the same time. Who cares? They don't depend on each other. The second add and the third add is dependent on the results of the multiply. So you build that dependency graph. You need to finish the multiply before you can do this second add right here and the third add right here, right? So that's what Dataflow is. It allows you to do things in parallel whenever you can. Now we're going to move on to the content of this lecture, right? Now that we do some quick overview of what we talked about last week. Basically, the way you design the ISS, think about it this way. I know physics. I know electrons. I know that computers store things using electrons in the capacitor. And from the capacitor, you either have the value of 1 or 0, and you have to control that. Your program manipulates the data from your input data to your output data, and somehow something control that. So from your program, Java, Python, C, any other language you want to use, right? You eventually, these are different language, but in the end, you need to be able to talk to the computer. So that's where the binary format comes in, right? Computer cannot really understand anything except for electrical signals, voltage value, in fact, like high volts or low volts. If that's electron, that's high voltage. If that's low electron, that's low voltage. And that's why you use the binary format. It's either a bunch of ones, a bunch of zeros. Right? And you can convert that to decimal. You can convert that to instruction if you look into the File Pro assembly 86 assembly assignment. Some of you will be assignment 3, some of you will be assignment 4. The one that convert the push and pop into binary, right? And do the disassembler, which is you have the binary, you convert it back to assembly. So you can actually use binary to represent your program, right? So the idea here is basically, hey, we know that we can convert everything in the program to binary. And binary is understood by computer because you can sense the high and low voltage. It means that now we can represent our human instruction, right? Human instruction that are in Java and C. Okay, I know that that's not exactly human, but at least it's human readable programming language. All right, basically you can convert programming language into binary format where commands are in binary and data are in binary, right? And use this binary format as the interface between your assembly code and your computer, right? Any questions so far? Okay, so now that we established what is an ISA, let's talk about what we call microarchitecture. And many of you would think of this as what is architecture, right? It's basically a hardware design. ISA define the language, the list of command, right? That tell, hey, hardware, do this. When I see an add instruction, I take two inputs and I add them together and I get the output. If I see a multiply instruction, instead of adding two numbers together, I would take two numbers, multiply them, and get the output. If I say if else, right? If I see if else in my language in ISA is branch or jump instruction, then you know exactly, okay, from this point, jump to this line of code, jump to this line of code, or just go to the next line, depending on the result of the if or else statement, right? This is defined by the ISA. The ISA tells the hardware how to do each thing. The microarchitecture is where the hardware resides. Basically, that's where you house all the hardware. That's where the circuits perform each command. ISA tell what are the commands. Microarchitecture tell what you should do, tell the hardware what you should do, as well as it house the actual hardware itself, right? So the microprocessor, the CPU that you buy, the computer that you buy, is ISA plus microarchitecture, right? And this microprocessor becomes the interface between software and circuits, right? Now that you have this interface, and you know that as a programmer, you program the software, right? And then with that software, there's a user. So you have this full, I guess, fully piped thing where you have the user, right? User use the program. The program actually becomes the ISA, right? Which then is run on the hardware. And this is where we use microarchitecture. I use the letter micro because I don't want to write. Basically, from this point on, whenever I say uArch, it's microarchitecture. Now you see that you start from the user, right? And somehow all the way you have this function hardware. User can use the hardware now with the ISA. You see the flow, right? From the user commands down to how the electron should move on your desktop, on your server. And let's dig deeper. What is inside the ISA, right? So the first thing that you see in the ISA is instructions, right? What are the instructions? Can someone tell me what do I mean by instruction? And you've seen it before for sure because FilePro and, well, no, actually, I have a quick question for your 69 and 60 student. This is a prerequisite for FilePro, or is this like, it's not, FilePro is not required for this class, right? Yay! That's screwed up. This is so screwed up that the order is super wrong, but I think they fix it. Yeah, just be aware the order is super wrong. It should be FilePro before architecture, no matter what. Anyway, so then let me explain it in. How many of you here haven't taken system skill? Because I think all of you did. Or FilePro 102. Nope, nope, nope. Okay, so good. All right. So instruction is when you see the assembly code in x86, those are instructions. So what is inside the instruction? What does the instruction tell me when you program it? If I look at the assembly, what can I tell? All right, guys, wake up, wake up. Come on, wake up. Not you, Pat. Don't jump on my keyboard. I mean you. Tell me what is inside. What is the information that I can see from the instruction? Are you there? Anyone there? So silent here. Awkward silence. All right, let me tell you what's in there. You see the opcode, right? What operation you're doing? And things like data type. You have addressing mode, right? And we'll go into what are these. It is instruction type and format. Is it a compute instruction? Is it load and store and deal with memory? And what's the formatting? You have register. Depending on each ISA, it deal with different register. You have the way that you manage the memory. It would define the address space. In your first assignment, you have to play around with that. Basically, you have to know exactly what address space you're accessing. You have things like addressability and alignment. Right? Things like, okay, can I access things in bytes, in words? Do I do a byte align or do I do word align? What is the difference between word and a byte? A word and a byte. I taught this in File Pro for everyone. I think almost everyone here. Are you giving it back to me already? Okay, awesome. Basically, a word depends on a system architecture, right? Think of it this way: a byte compared to human language, a word consists of multiple characters. A byte is kind of like one character. A word in computer science, it depends on the type of machine, as Brandon said, right? If it's 32-bit machine, a word is in 32 bits or 4 bytes. 64-bit machine, that becomes 8 bytes, right? And a byte is just a single byte. There's also, we would specify virtual memory management. This is one of the important aspects when you have things running in the cloud and when you have to share amongst multiple programs. You have the way to manage the system call, right? Interrupts, exception handling. So if you do any type of program, you see things like seg fault, right? Seg fault is a type of basically it's an exception that caused by your program. It happens because there's something wrong with your code. Other type of exception that can happen involve things like you intentionally throw an exception because you detect things like divide by 0. Interrupts are things like when you type on the keyboard, it's an external factor that kind of like impact your program. Someone type in alternate tab. TOS has to handle, okay, alternate tab means I'm going to switch a program. I would do that. Calls, things like function calls, how do I manage that? Access control, like should I be able to access to the kernel space or should I not be able to access kernel space? Priority and privilege. These are things like, let's say you want to run 8 different programs in the 4 core machines. You will then look at the priority, right? The command that send a printer job is probably less important than the command that try to compute something on the game that you're playing, right? The I/O, the ISA would specify how you interact with the I/O, how you would manage the threads, how you actually manage and control power. This is one important aspect that many people forgot, that the CPU can operate on different power and thermal mode. You can actually slow down the CPU, right? You can slow it down and now it will consume less power. What does that do to you? Let's say you're on a mobile phone and you want to save power. That's what the low power mode is doing. It look at, okay, can I disable some of the things and I actually put the components in the lower power mode. Everything will become slower, but hopefully your battery lasts longer. This thing exists. This thing is being done all the time. All the time. I can tell you this happen all the time when you run a program on a desktop, when you run a program on the phone, and when you run a program on a server, right? These things consume so much power these days. You can actually, sometimes you need to have a small power plant stick next to a server farm just to actually power all the servers. All right, now we talk about a little bit of the high level overview of the ISA. Let's move to the microarchitecture, the actual hardware. As I said, ISA defines what the software can do and tell what the hardware should do. The microarchitecture basically it implements what the ISA is specifying with some trade-offs, right? One big thing is everything that you do, everything you design inside the hardware is transparent to the software. Have you heard about any of this terminology before in this bullet point? Anyone heard about any of these things before? Pipelining. Okay, good. Pipelining is done in our processor. It makes your CPU actually a lot faster. When you program as a programmer, you never realize this thing exists, right? This is what defined as a microarchitecture. It's a implementation of your hardware to make things faster without the programmer knowledge. That's why when you buy new chip, like the new CPU, even though it's clocked at almost the same gigahertz, sometimes it's actually a lot faster because of they change these design. They change the design of all these components so they are more effective. So even though you clock your CPU at the same rate, everything becomes a lot faster, right? One thing from last week lecture that I talked about Spectre and Meltdown, the hardware bugs, right, that can cause people to hack into your system, is a result of this speculative execution. This caused things like Spectre and Meltdown bug, right? And when you disable this, your CPU becomes slower. This can be done to save power. For example, right? You actually look at the program you're running, and somehow the OS, the operating system, would work with the CPU, saying, "Hey, I don't care about the performance of that program. I'm going to power down." Or I'm going to say, "Hey, I care about the performance of this a lot because this has higher priority. I'm going to power up things." Right? The OS and the driver would manage that. Things like error correction, this is done automatically in DRAM. How many of you run into blue screen? I think all of you, or potentially all of you, have run into blue screen before and it reboot your computer, right? A lot of the really, really common cause of your blue screen is because something flipped in DRAM. There was some error in DRAM. This error can happen from basically I have a really weak capacitor and just suddenly by chance flip itself, electron leaks out. There's also sometimes there's a gamma particles around in the environment just happen to hit directly into that capacitor. It bumps the energy level. Electron moves out. Those can happen as well. So this thing can cause the blue screen, right? So you can have error correction to make sure that's less frequent, right? Bit flips, I guess errors from bit flips. It actually allows you to correct the error on the fly. You see one bit flip, this logic would detect, hey, that bit is flipped. I'm gonna correct it back. That's it, right? You can inside the hardware. There's a logic to handle that. There's so many other things that we do to improve the performance without most software programmer realizing. So what are the trade-off, right? The design trade-off. Think of it this way. You are now in this class, everyone has a hat of an architect. What does architect do? We design things, right? We design the computer. The real architect would design buildings. Us, computer architect, we design computers. So there's a lot of design trade-off that you have to think about, right? What would be a bit pattern, for example, if you use floating point 32? How many of you heard about this format? TF32, TensorFloat. This almost, I would call it bullshit terminology from NVIDIA. How many of you heard about that? Silent, I guess no one heard about it yet, right? Basically, what NVIDIA in the most recent architecture that they came out, they said, hey, we've been using floating point 32, right? It used 32 bits, and it would cover this range. So this is FP 32, right? This is negative minimum, and then the maximum value that floating point 32 can cover. And they said, hey, when you run things in machine learning using TensorFlow, you don't care too much about the accuracy. So instead of using 32 bits, I'm going to offer the same negative minimum and then the maximum using a 22-bit format. So each tick is wider. It would then cover the same range, but then you lose accuracy. The reason why I hate the naming is actually I kind of hate NVIDIA PR team all the time because they have been using super unscientific terminology that breaks the convention and confuse the heck of a lot of people. Is that this is actually 22 bits. What's the point of saying 32? Because 32 is specified 32 bits, right? But basically, these are the design trade-offs that say, hey, I can have a floating point representation that covers the same range using 32 bits. I would rather have them call TF22 and say, hey, it's cover the same range as floating point 32. Number of register in x86 versus ARM, right? How many registers do you have in x86? Anyone still remember? Yeah, you are right, 16. 16. So you have 16 general purpose register. In ARM ISA, you have a few more. And then you can context switch. So each process gets its own copy of register. In the lab, with the ISA that we would use for the lab, you have 32. So these different number of register offer different trade-off. The more register means that you have to have more transistor to implement the register. But then you have more flexibility of, okay, I can use this register 1 to 31. I have more register. I have more temporary value I can use for my program, right? Number of ports. What does port do in real life? It allows the ship to dock, right? And transfer the content of the ship to the docking station. The port in hardware serves the same purpose. It allows you to actually transfer data from one hardware to another hardware, from the wire into the component itself, right? And number of ports to the register files means that, okay, can I access different register value in parallel or do I have to wait? Do I have one port? It means that each ship comes in, that had to be transferred, go out, the next ship can come in. Or do I want to have two ports? I can dock two ships at the same time. I can see and I can read two values at the same time. The number of cycles to perform one, say, multiply instruction, right? You would then figure out how do I design the microarchitecture. This is a microarchitecture where you say, okay, if I have multiply instruction, do I want to actually put more transistor to make it really fast? Or do I just want to have fewer transistor and save it for something else? And what happened with ISA changes? Right? And this discussion gets more important these days. You might have noticed as Apple Silicon, right? That are coming out probably next year with ARM processor. ARM is different from Intel, which means that you would have to think about the way to communicate between one MacBook that uses the Intel chip and the other MacBook that uses the ARM processor, right? As I said, ISA is a language for the computer. One hardware knows only one ISA. It means that computer cannot, stress on the word cannot, understand the executable, the binary, compiled with the different ISA. So if you have a source code, right, program with source code, need to be re-optimized for a different ISA. If you don't have a source code and binary is the only thing you have, you're out of luck. It will kind of will stop working unless you do something with it, right? The first thing you can do, if you have the source code, you will then recompile the code and get the optimized version for the new ISA. You can also do this thing called code transformation, where you transform the executable of one ISA into another ISA. Can anyone tell me the reason why code transformation can be complex? Anyone want to take a guess? Are you still here? Anyone still here? So quiet compared to OPL on Friday. And I know there's only like 7 of you, so it's totally understandable why it's more quiet. But anyone want to take a guess on why code transformation can be complex? The answer is basically there's no one-to-one mapping. There's a compatibility. Yeah, yes, compatibility issues. The reason behind it is there's no one-to-one mapping between one instruction into another, right? Let's say these areas support 3 different type of ads. The other one support 4. How do I know which one of these ads maps to the other one? So you kind of have to look at the binary code and somehow know what this program is doing before you do the transformation. We need to extract the semantic information. We call this semantic information, which is basically what the code is doing so that you can transform it to a different ISA. So in conclusion, you might have noticed there's so many programming languages, there's so many scripting language. If you look at the front end stuff, I would I actually personally I don't understand why so many different type of library framework and languages for the front end stuff. I think that's kind of too many. But if you look at the ISA, there are not going to be a lot of those. When you boil down after you compile your code, what are the common ISA? x86, ARM, RISC-V, which is coming up, like up and coming ISA. Back in the day, there's MIPS, which is what we do in our lab, and that's it. Not much, but there's like there's actually quite a lot of old ISA that no one uses anymore. There's a Power. IBM Power is another common ISA used by IBM Server. That's Spark, right? And that's pretty much it, right? Not a lot. Probably most of the time less than 10 across the globe, right? And each ISA gives you different trade-off. That's why you have more than one ISA. There's nothing that like basically there's no ISA that's perfect, right? There are things like complexity of instruction, how each instruction is specified, because the assembly code would look different. Are you trying to support different features? There's SIMD, uh, SIMD plus FMT, fine-grained multithreading for the CPU side. Do you want to somehow give the ability for the programmer to lower the power or use a low power memory, or like operate on a much smaller memory? Uh, and there are 2 types generally of the ISA. Have you heard about CISC versus RISC? Complex ISA versus reduced ISA. These are the debate amongst like architect of the old days, that hey, each one of these offer different things that trade off, so which one should be used? What is x86? Is it a CISC or is it a RISC? Anyone want to take a guess? It's only 2 choice. Come on. For Intel processor, which one is this? It's a CISC. Yes, you're correct. This is where x86 is. In our lab, for our assignment, you are going to implement MIPS, which is a reduced ISA. I'll tell you why we picked MIPS instead of x86, and I think you'll be glad. The instruction, if you break it down, is the most basic elements of the interface between your software, your program, to the hardware, right? And these are the main components. If you want to get anything out of today's class, remember, in an instruction, there's an opcode and there's operand. I hope at least you get these two things. The main component of your instruction, opcode and operands. Opcode is a binary pattern that tells what the heck this instruction is supposed to do. Operands means that for this instruction, what is the input and what is the output? Who has to perform the instruction? For example, this is a fake ISA, right? But let me define it as this. When I say add R0, R1, R2 means that I'm gonna have R1 and R2, add them together and put the result into R0, right? So over here, R0, R1, R2 are the operands. Add is the operators. That's it. Any questions on this? This is what I want from today. Basically, when you look at the instruction, you look at, okay, these are the action that I have to do, and these are the object of my action. What has to be doing what? That's opcode and operand. And then there are different elements of the ISA, right? Sequential model will tell you whether you use control flow or data flow for the purpose of this class. Most of the things we talk about will be in a control flow sequential model, right? The processing styles, back in the day, you can have different number of operands. These days, you're focusing on these two address and three address machine. Two address means things like Intel x86, where you have operand, source, destination, right? So these are things like x86. And I believe like this, for example, is MIPS, right? What you would do is in the lab is a lot simpler. You have source 1, source 2, and destination. I think RISC is also this in this type as well, RISC 5. I believe this type. I might need to double check that. If I'm wrong, I'll let you know. I'll correct myself next lecture. But I'm pretty like 95% sure it's on the 3 address machine. Basically, you have source 1, source 2, and the destination is well declared. And what are the trade-offs, right? These are things like space and performance and code size. Why would code size be important? Anyone want to take a guess on why should I care about the code size? Yes, it fits on a much smaller machine. For example, my Apple Watch, right? It's tiny. I forgot the spec already, but it has a much smaller DRAM than my desktop, obviously, right? So the code size for programs built for Apple Watch has to be a lot smaller than the one on desktop. When you compile a program in a small small embedded devices, you don't want your program to take up like 20 megabytes or like 10 megabytes because that's so much on those machines. Most of those type of embedded devices, you don't have that many megabytes of DRAM, so you want small code. There's also other, as I said, there's a operand and opcode and operands, right? So operand specifier. How do I use the operand? Basically, operand specifiers is kind of like how do I use the operands? The data type. What does each of the bit represent? Are they integer? Are they floating point? Are they character? Are they binary? Or somehow are they decimal number? Most of the time it's not decimal number. But you can build an ISA of your own that read decimal number, which kind of looks would be looking odd, but yeah, you can do that too, because now you are the architect. You can design your own hardware. You can have a complex data type, such as x86 or wax. Wax is like super on. If you look at CISC versus RISC spectrum, wax is for n the extreme of the complex instruction. If you can think about something, there's probably a likelihood that instructions support what you think in wax, right? And will tell you what are the trade-offs. Here you can have complex instruction, right? For example, you can have one instruction to say, hey, this instruction compute a convolution. What is a convolution? It's series of multiply and add. It's used in image processing. It's used in machine learning. CNN, if you have heard about it, yes, that's convolutional neural nets, right? So it performs a bunch of convolution, multiply, add. It performs a bunch of metrics multiply as well. You can do an instruction that load an entire array. This can be pre-built to CISC. Alternatively, you can also build like random chip, not random, but like a lot of companies these days, Apple, right? They have this machine learning chips. I am aware that Alibaba, for example, is also building a neural network chip. I'm sure Huawei also is doing that as well. Most hardware company would have this thing called special purpose chip that's built to do certain things, right? And they can be loaded with this complex instruction that say, hey, do the convolution on that chip right there. It would send the data over, and that chip would perform things like CNN or deep learning or graph convolutional network. I think I haven't seen the GCN one, but I've seen things like RNN. I've seen things for CNN on a chip before. RNN, I think it's a paper from last year. CNN is about like 6 or 7 years ago. It's actually an old technique now. That's why you see it as a product. That's also like for example, I have a project with a student in Shanghai Jiaotong that look into recommendation model, things like what Netflix is suggesting you watch this, watch that. Most of the time it's not really effective, but still they spend so much time browsing Netflix on what to watch. But those things is now being targeted toward your mobile devices, your embedded devices, right? The low power method to do this recommendation system is another emerging technology. You can look at simple instruction, right? Everything go back to things like add, multiply, export, load, and store. Simple. And complex instruction always can be built from series of simple instructions. And here are the trade-offs. If you look at CISC, right, or complex instruction, you have a smaller code size because each instruction can do more things. Each instruction is more complex. You can have a simpler compiler. It doesn't have to map a lot of like program into a complex task. There's an instruction for that. For the reduced instruction for CISC, it's simpler in terms of the hardware design. You only have to perform simple instruction. You can clock it really fast, so you get higher frequency. And this gives room for the compiler to do a lot of optimization. So hopefully, if you rely on RISC, you have a good compiler that would optimize your program for the assembly language that you're running on. And here are some more trade-off. RISC, right? RISC is MIPS. MIPS is what you're going to implement in this class. There's like Alpha 21.264, CISC 6600, and RISC-V. RISC-V is what is gaining a lot of popularity these days in startup area as well as emerging company. I know that Alibaba, for example, is actively looking at RISC-V. I'm pretty sure Huawei is also actively looking at RISC-V. A bunch of startup company in the US is also looking at RISC-V. Why is that the case? It's open, it's free. This is the push coming from university, mainly from Berkeley, on make the ISA open. And RISC architecture is simpler. Why? Each instruction do simple thing, and you have transistor, right? So because transistor is limited to support just this set of simple instruction, you are going to dedicate less transistor for that. What does it mean? What does it mean if I'm gonna dedicate less transistor to support the instruction? It means that I have spare transistor to make the computer faster, essentially. I would have spare transistor for optimization. And then the compiler, as I said, optimize the code, right? If you look at CISC machine, like x86 or VAX, you can have fancy code, things like this. There's an instruction called repmove-s. This is a real instruction in x86. What it does is you're going to put a range of array, basically array of data, and this instruction would perform a move instruction on that range. Just one instruction in just one instruction. It's designed to close the semantic gaps, the gap between the program, the high-level program to the hardware. But because you need to support this complex operation, you're going to spend the transistor area to support these complex instructions, right? Generally, another benefit is we have smaller program size. And let's talk about the semantic gap. Semantic gap is the gap between what the software is doing and what the ISA provide, right? A large semantic gap means that you have things like RISC ISA, where instruction control a set of control signals, and the compiler generates this instruction to control the computer, and it allows more, right? More compiler optimization, more fancy things coming from the compiler. Small semantic gaps mean that each instruction somehow looks like a high-level language. Add a node inside the linked list can become an ISA instruction. Copy the content of this array into this array can be one instruction, right? You allow more application-specific hardware optimization, things like let's do a convolution, for example. And you can always translate one ISA to another ISA. As I said earlier, you can do code transformation, and that changes the semantic gaps. This can be done either in hardware or software. And different data type also offer different trade-off, right? You can have high-level data type. What is a high-level data type? Anyone want to give an example? Let's say I want an array. Is that a high-level data type? Yes, because it consists of multiple words. It has certain length, right? Which means that you have to specify the actual array and somehow tell, hey, that's the length of my array. The trade-off is also you have to build some support to make the hardware aware, hey, that's an array, that's a linked list, and that's a graph, right? And these data types are kind of tied to the semantic level of what you want to support. Any questions about data type and semantic gaps before we talk about what goes into the ISA besides opcode and operations? Any questions? No? Okay. So let's move on, right? Wake up. Anyone need a coffee break? I know it's been an hour and I know I've been monologuing. Okay, let's do a coffee break. We'll meet in 5 minutes. Is that okay? Is that too little? I can do 10 minutes too. Okay. All right. So we will meet at 1:10 p.m. Let's go get coffee. I hope we come back and you are a little bit more awake. I'm not expecting you to be wide awake, but please be a little bit more awake and respond to my questions. Okay, so let's do a 10-minute coffee break. We'll meet at 10, no, not 10, 1:10. All right? In the meantime, if you have any questions, feel free to ask. Sure, yeah. So let me put it this way. Semantics. Have you heard about semantic versus syntax? You've heard about the two both terminology, right? By heard, I mean you've seen it somewhere before. So think of it this way. Let's say we write something in English, right? Let's say I look at one paragraph. Syntax means whether you have a correct grammar or not, right? You have a correct structure of the sentence, subject, verb, object. Subject and verb has to have the subject verb agreements. I am, you are. You can't say you is, right? It is wrong grammatically. So that's the syntactic information. Do I have the correct syntax? In programming, syntactic information are things like, do you forget semicolon? Do you open parenthesis, forgot to close it? Why is that important? Because basically the compiler has to know has to know what you're trying to say, and it has to be correct. Otherwise it becomes ambiguous, right? It becomes ambiguous. Semantic information is when you string together the program. When you string together in a paragraph of English, you would know what the paragraph means. If you have no semantic information, I'll just string together random sentences in a paragraph. And when you read it, you'll be like, what the heck am I writing? Right? That means that I have given you no semantic information. Semantic information would tell, if you read that paragraph, you would get the picture of what I want to say. The same thing goes to your program. If you analyze your code from this line to this line, semantic information would be able to tell you that, okay, this part is insertion in a linked list, for example. You know what is the high level operation. So that's what semantic is. So hopefully that is more clear with, between like what semantics and what syntax, right? Okay, cool. All right, and we are right at 1:10. So let's go. Hopefully you guys are all back. Get coffee or at least some caffeine. I don't know, like get some snacks. Make sure you're awake. I know it's boring. I know that the lecture can be boring. I'm trying my best to make sure it's less boring. But if you get lost, you either ask a question as soon as possible, or go watch the video and ask me questions on Discord. I would go there and tell you what's going on. All right. So the next set of things that ISA needs to specify are, how do I deal with the physical memory? How do I deal with DRAM, right? You need to figure out address space situation, number of unique locations in the memory, who does each thing belong to. Basically, let's say you look at this block, this region of memory, is it belong to where you store the code? Does it belong to where you store the data? Does it belong to the data of this process versus the other process you're running on the computer? Right? You need to think about addressability, right? Do you want to be able to access each individual byte? Do you want to be able to just support each word accesses? Or do you want to support each individual bit? So one exercise you can think about, and hopefully to give you a little bit better picture in this, is like, how do you add to 32-bit number, but you only have byte addressability? You can't access the whole 32 bits. Versus, how do you add to 8-bit numbers, but you can only access a 32-bit chunk? Both of these cases are not trivial. You can't just say A plus B. In the first case, you need to extract each byte 4 times so that you get all the 4 bytes and then add the two numbers together. You would add the first byte, look at whether they have a carry. If there's a carry, you add the second byte plus 1. If there's no carry, you add the second byte without the plus 1. You do that for all 4 bytes. maybe I should do this as an in-class exercise. I didn't put it this way in the in-class exercise. There's nothing related to this, but please go through this practice. It would tell you then that when you deal with different granularity of the data size, you have to think a little bit. Basically, you have to think a little bit and figure out, is that correct? It's not that mad. I mean, come on. Hardware has its limitations. So when you have instruction, you have to figure out which byte are you getting. So you just basically, what I'm telling you is you have to be a little bit more careful based on the addressability, right? How do you want to support virtual memory, right? There's also the issue of big versus little endian, which we'll discuss later, right? Big versus little endian. We talk a lot about this in FilePro and system skill. So I'm going to kind of not talk about it now. If you have questions about this, let me know. I'll assume you all took that class. It's kind of like always, it's a prerequisite for this class. And by this time, hopefully you are familiar with it. The element of the ASIC, what are the other elements of ASIC? Register. What is a register? Think of it as a really, really fast temporary memory. How fast? One cycle fast. So if your clock in the CPU is say 3.5 gigahertz, that's about 0.3 nanosecond to access the data. The issue here is like how many do we need, right? To be honest, the more the better in terms of programmability. It's easier to program, but then that consume transistor, right? How big should the register be? Should it be 16 bits? Should it be 32 bits? Should it be 64 bits? This helps support when the case we have data locality. We'll talk a little bit, we'll talk a lot more about data locality when you go through caching and the memory hierarchy. And there's a evolution register that I want to put you in a more like historical context. Back in the day, you can't just say, hey, this thing would take number 5. You start from 0, you accumulate 1, 2, 3, 4, 5. You actually need to write a program to accumulate it. Then you can specify the address. And these days, we call we now have what we call general purpose register. Our hardware evolution is good enough that you can design a register that can take any type of data. It's easy to use and easy to modify. And it ranges from a few register to something like 128 in Intel 64-bit machine, right? And these days, these are the only thing you see. It's called general purpose register. You don't see the first and the second thing anymore. It is too simple and it's not exactly useful these days. You can build a GPR really cheap these days. You can have thing called addressing mode, which is one of the element of the essay. You need to specify that. What is addressing mode? It tells you how do you get your operands, right? You have the operands, your input to your operator. You can have the absolute version, which is say load R010, right? You have the absolute value 10 here as the input, right? So this means I'm gonna load value at address 10. You can have register indirect. It means what it means. You use the register value as the value you want to access here. Instead of address 10, right? Instead of address 10, let me use a different ink color. Here, you now use bracket, pen. I'm using pen, so give me pen. I'm using the parenthesis R1 to specify that I'll take whatever R1 data is, use that as my address. The last type is called displacement of base. Basically, on top of just using the R1 like this, right? This part is similar, but you also have the offset. So you have offset plus the value of R1 as the address that you want to access. And each ISA has a definition of how you want to have its own addressing mode. It would tell you exactly how this should be done. You are the designer now. If you design the ISA, you just tell this is how it should be done. If you're implementing the ISA, you go read the report and say, okay, this is how you implement it. It would tell you exactly how this is done. What you learn, all the rules that you learn from file processing plus the system skill class, those are for x86. x86 addressing mode is different from the other ISA. So the key is you go read what the ISA specify and you follow that guideline. Any questions about this? So there are trade-offs between each addressing mode, right? The more addressing mode you have, it reduces the number of instruction and the code size. And some type of access are better suited in certain mode, right? So let's say I have an array. What type is good for an array? What addressing mode is good for an array? So I'm going to go back one slide and show you that addressing mode. Which one of this is good when you use with an array? So let's say I have array, right, that consists of 10 elements. Anyone want to take a guess? Displacement, correct, right? Because you can put a 0 right here. And this value can be just 0, 1, 2, 3, 4, 5, right? So this is compatible with array. Pointer chasing, maybe this is displaced. This maybe this indirect is good, right? Because what is pointer chasing? Things like linked list. Like linked list means that I need to access this element and that element would tell you where is my next element. So you can use indirect as an addressing mode for linked list. Some of the downside of more addressing mode is when you design a compiler, you need to program the compiler to be more complex. These days the compiler is good enough to handle model addressing mode, so don't worry about it. These days compiler technology is really good. Also more work for the microarchitecture. Like we need to design a hardware to support every single thing that we say we want to support. Another element, how do we interface with I/O? There's this thing called memory map I/O, right? It's a region of memory that's mapped to certain devices. For example, I can say this region of DRAM represent what pixel on my monitor should the value of each pixel, what's the color that go into each pixel, I can map it to a region of my memory. Right? This allows your processor to store the data and allows the I/O devices to look directly into these data. So you can imagine you can use this for different keyboard input, different type of monitor, right? You can have special I/O instruction to deal with the I/O devices like hard drive, SSD, right? When I have this instruction, do I go and spin the disk to seek the correct files? How much do I go and seek it? What's the angle that I'm going to read from this spinning disk, right? There's also things like privilege mode, the user versus supervisor, right? Who controls what, who executes what, how to handle exception and interrupts, what to do after you see exception or interrupts or something goes wrong, check for example, what do you do? What happened if someone type on the keyboard? There's also vector versus vector interrupts. We're not going to talk about this in detail. It's a content for operating system class. Definitely not going to talk about it. Virtual memory, we'll talk about this in detail in this class. It's actually a lot of both design trade-off in hardware as well as in the OS. access protection. We'll talk about this in this class as well, pair up with the virtual memory. So this is later in the second half of this class. Well, I don't know. I mean, I'm not that good at I never teach OS before, so and I think Ajahn Sansan did a really good job teaching OS. OS is just OS, right? So it's pretty unique in the sense that, I mean, it's hard. So if you take the class and say, hey, that's hard, it is what it is. There's also a class of different instruction, right? Operate, like compute, right? Compute instruction that do arithmetic or logic operation, add, and, or, XOR. Data movement, where you store data in DRAM, talk to the I/O, get the data from DRAM, put that into register files. Then the last type is called control flow instruction, where you change the sequence instruction you are running. What where do you go when you have the jump? Where do you go when you have a branch, right? That handle things like if else or for loop. Another trade-off that you have to kind of understand is like a load store versus memory to memory architecture. The load store architecture means that you deal directly with the register. You put data from the memory to the register, put the register data into the memory, right? You do compute, and many of the RISC ISA is a load store data architecture. Many of the complex ISA support memory to memory, which means that you can operate directly on memory location. Let's say I want to copy, right, this array 1 into array 2. Your instruction would somehow be able to tell this, copy from array 1 to array 2. The complex ISA would basically build the hardware to do this support. You specify the array 1 location and array 2 location, done. The load store architecture, you would have to load the value, load the first. Basically, over here, if you want to do this in the load store architecture, like array 1 and array 2, what you have to do here is you have to go through each component. These go into register R0 and then write it here, followed by this, write it to here, followed by this, write it to here. So you do it one at a time using the register as the interface in the middle. Memory to memory, you can do it right away from one location to another. And that trade-off, right? The trade-off is you need to build the hardware to support the memory to memory architecture, which sometimes doesn't get used, depending on how you utilize these special instructions. There's also instruction length if you do the lab. If you do the lab in file processing / system skill, the lab that has assembly code, one of the assignment we asked you to support different push instruction, right? And you notice that these different format use different number of bytes. Sometimes it's 2 bytes, sometimes it's 3 bytes, sometimes it's 4 bytes. You can also have a fixed length instruction, which is for everything in your ISA is going to have these many bytes. Everything would be the same. This is easier to decide what you're doing, easier to decode to figure out what instruction is doing, because you don't have to figure out, okay, how many bytes is this instruction? But you can waste more bits, right? Which means that you can have longer code. Not longer code in the sense of like more instruction, but longer code in terms of the size in bytes of your instruction. And this is generally harder to extend. Let's say you want to extend your ISA into a much bigger ISA. Sometimes you just ran out of bits. Seriously, you just ran out of bits. And this is an example from RISC-V architecture, right? You see that everything here is 32 bits. And you also support 16-bit formats, but you will need to tell the program would need to tell the architecture, hey, I'm using a 32-bit version. So every single instruction is going to be 32 bits long, right? You can have the variable length where you have a more compact encoding. Some instruction that doesn't need 4 bytes, you would use 2 bytes. Some instruction that doesn't need 2 bytes, you would use only 1 byte for that, right? But it's harder to decode. And here's an example. x86, which you learn in file processing / system skill, is a variable length format, which means that sometimes instruction is 3 bytes, sometimes it's 2 bytes, sometimes it's even 4 bytes, right? You can check out the manual right here to see each instruction. It will tell you exactly these are the opcode, and this, if you've seen this pattern, you check for the next byte, or if you've seen this pattern, you check the next 2 bytes or 3 bytes based on the pattern that you see. And that gives you a trade-off, right? On decode. Decode means I'm trying to figure out what my instruction, the bits that I see, what are they doing, right? If you have uniform decode, the same set of bits correspond to the same thing. This is easier on the hardware design, and you can have more parallelism, but as I said, it's waste instruction space. Non-uniform decode, as I said, you can make it more compact, right? You can have variable length instruction size, easier to extend, but more complex decoding logic. Why is it more complex? Over here, you don't even know whether you see the first byte, right? And you have to figure out, okay, do I get more bytes or am I done? Right? Do you get 1 more byte or do you get 2 more bytes? If you get 2 more bytes, then you would grab 2 more bytes. Otherwise, you only grab 1 and figure out which bit means what, right? So that's the non-uniform decode. That's a trade-off, but then your code can be smaller. All right. So that's the end of the theory side today. I think I hit the mark that I want to be in the 1.5 hour. Today, we're going to talk a little bit about your assignments and the whole class, the whole semester. We'll talk using MIPS R4000. What is MIPS R4000? It's an ISA that is a lot simpler than x86. From what I've heard, this class that I teach at MUIC before I took over, I think it was being taught in x86, and that's a really, 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 really bad choice. I can't stress you how bad it is, because x86 is complex. As a way to design the hardware, you never want to start with x86. That's why I picked MIPS R4000. It's a lot simpler. It's actually used in most university as the default ISA to learn architecture, right? It's actually used commercially back in the day. How many of you had like a PlayStation or a Nintendo 64? I know it's a long time ago, but if you happen to have them, they are implemented in MIPS ISA. PlayStation 2 is MIPS, I think, are 8,000 or 10,000, or I think one of either 8,000 or 10,000. One of those two. It's a newer version of MIPS architecture. Both PlayStation 1 and PlayStation 2 use this architecture, which kind of means that if you have those old games, in theory, you can use the binary from those games and run it on your simulator. And technically, if it doesn't use odd instruction that you did not support, it should run. So this is the go-to ISA that we are going to use for the purpose of this class. Why is that the case? It's really easy to create a design for this ISA, a design that's functional. I'm not saying a design that performs well, a design that's functional. So you can learn when you need to build a ship, this is what you do. Right? And you can see the full detail here. This document is something that you need to go through anyway when you do the lab, because it will tell you exactly, okay, if I see this instruction, do this. If I see this instruction, do this. It's long, but it's super easy to understand. Basically, we will tell you, if you see this pattern, do this. If you see this pattern, the hardware is supposed to do this. If you see this pattern, the hardware is supposed to do this. And the way it works is it has 32 general purpose register. It has a separate program counter, which we'll talk about next lecture. On lecture 3, what the heck is PC? And it has status register. It has a physical memory. It manages the physical memory by dividing them into chunks, or text, which is where your program is located. Data, which is where your statically allocated space is declared. Things like array that you know the size beforehand. So when you compile it, you can statically allocate them. And it has another space for your stack. The stack is your dynamically allocated space, right? And what I want you to do today for the rest of the time until 2 o'clock is to look at this available simulator. It's called SPIM, and here's what it would look like after you install. I think this is the Linux version. There's a version for Linux, there's a version for Windows, and the version for Mac. Pick the one that corresponds to your machine, and I hope you can tell what your machine is. So pick the one that you use. And here's the location of the simulator. Download it from here. Basically Google this. Google XSPIM. Why is it XSPIM? If you reverse this, it's actually MIPS. It's MIPS simulator. And they just flip. I don't know why they do this, but yeah, they reverse the letters. And X stand for graphical interface. Basically, it allows you to see, okay, when I run this program, this is what changes. Here's the manual. And oops. No, get rid of this. I got rid of this. This is actually for Wednesday. So once you have this installed, one Wednesday, we will do a simple program, just adding two numbers together and perform a factorial. Don't worry about is prime. That's not required. And please fill in the poll for the class. I want to figure out whether you're free at what time, so we can have office hour as well as a potential slot whenever I have to reschedule the class, so I know that, okay, I can go through these times. So that's the location of the poll. I don't want you to copy it from here. It's a lot of letters. Go through the Canvas announcement. It's over there. All right, so here's the in-class exercise. That's it for the class today for the lecture part. Any questions? I hope you are excited to some extent about building a simulator for a real ISA. Right? Basically, this would be what we do for the assignment in this class. We will actually build a simulator that would actually run a real MIPS assembly, a real program, and you see the changes. You see your hardware that you design make changes and actually produce hopefully correct results. And then you can tell people, hey, I built a simulator for a real ISA. And it's not that bad. I'll make sure you make progress. I'll make sure I tell you what's going on. Don't be scared ahead of time. It's not that bad. It's not that bad. Trust me. All right. So if there's no more questions, let's do the in-class exercise. Go and install this thing based on your machine. And there's a manual on the link. Basically, if you Google XSPIM, you'll see the link. And when you see the link, download and install it on your work machine, depending on the OS. Pick the correct one. Any other questions you want to check out? Otherwise, I'm gonna migrate over to Discord for the rest of the time until 2 p.m. So that we can do Q&A. You can share the screen, and I'll stop the recording right now. Okay, seems like no more questions.